Welcome back to the Deep Dive. Today we're really focusing in on something crucial for your professional journey. This is part of our CSWIP 3.1 exam prep series. Now, for those of you who may be new to this, CSWIP is the certification scheme for welding inspection personnel. And that 3.1 certification, well, it's the key standard for experienced welding inspectors. Our mission today, it's pretty clear. Tackle some real exam-style questions, multiple choice ones, and maybe more importantly, help you understand not just what the answer is, but the solid why behind it. That deeper understanding, that's what really makes a difference out there. Okay, let's unpack this.
Exactly. You know, it's one thing to memorize for a test, isn't it? But really grasping the principles, that's where the real value lies in welding inspection. That deeper understanding, that's what lets you apply the knowledge effectively in the field, makes you a much better inspector. We're aiming to build that solid foundation, you know, something that helps your whole career, not just getting through the exam.
Absolutely. Couldn't agree more. So let's jump right into our first scenario. I'll read the question and the options nice and clear, nice and slow. Be a moment to think before we reveal the answer and break down the reasoning. Right, first question. This one's about managing that tricky business of heat, especially on thinner materials. When welding thin plate, distortion can be minimized by, is it A, welding from both sides, B, using U preparations rather than V types, C, using strong backs, or D, using backstep welding? Okay, take a second. Think about thin materials. Heat control is so delicate, isn't it? Too much heat in one place, and, well, things can go sideways pretty quickly. Which of these techniques feels like it directly tackles that distortion from focused heat?
Okay, the correct answer here is D, using backstep welding.
Backstep welding, right.
Now let's break down why that works so well for minimizing distortion, especially with thin plate. Backstep welding, it's quite a clever sequence, actually. You put down short weld beads, right?
Yeah.
But you move in the direction opposite to how the whole joint is progressing.
Ah, okay. So if you're welding left to right overall, each little bit is right to left.
Precisely. You weld a short segment, say right to left, lift off, move forward along the joint line, and then do another short right to left segment. And the reason this is so effective is it helps spread the heat input out much more evenly. You're not getting that continuous linear buildup.
Right.
Instead, you're constantly shifting where the maximum heat is concentrated. This really cuts down on the total heat buildup at any one spot. And that's just crucial for stopping too much shrinkage, which, you know, is the main driver of distortion in thin plates. It's all about managing that cooling.
Okay, so it's not just less heat, it's about strategically managing the cooling, kind of breaking up that thermal wave that pulls things out of shape. But what about, say, skip welding? That also jumps around, doesn't it? Or even strongbacks, option C, just physically holding it down. How is backstep different, particularly for thin stuff?
That's a really good point. Skip welding, yeah, it definitely helps distribute heat too by welding in different spots. But backstep, it gives you maybe a bit more localized control within each segment. You're allowing the bit you just welded to cool a little before you heat up the area right next to it. Strongbacks, well, they're physical restraints. They hold things in place and they are used often alongside welding. But they can also introduce stress, right, which might cause problems later. And if they're too rigid on thin plate, you could even risk cracking. For thin materials, that localized controlled cooling from backstep often does a better job of preventing that initial buckling or warping right as it happens. It's like investing a bit more technique up front often saves a lot of hassle trying to fix a warped part later.
Makes sense. So the insight is really about managing the cooling locally, preventing that continuous shrinkage front. For inspectors, it's a good reminder that sometimes the slower, more broken up approach is actually the most effective for quality. Okay, from the physical effects of heat, let's switch gears a bit. Let's talk about the invisible chemistry, the gases we use to protect the weld. Our next question looks at gas metal arc welding, or GMAW, specifically for aluminium. A suitable gas-gas mixture for GMAW of aluminium is it A, 100% argon, C, 80% argon plus 20% CO2, or D, 98% argon plus 2% O2? Now, aluminium, it's a bit different, isn't it? That oxide layer, the way it conducts heat, it throws some challenges at it. So thinking about those unique properties, why would it need such a specific shielding gas? What's going on during the weld?
And the correct answer this time is B, 100% argon.
Pure argon.
What's really fascinating here and fundamental is the link between the material, in this case, highly reactive aluminium, and the shielding gas you need. Aluminium forms that tough oxide layer almost instantly in air. For GMAW, you absolutely must have a shielding gas that is totally inert.
Meaning it doesn't react.
Exactly. It doesn't react chemically with the molten metal or the hot surrounding area. Argon is a noble gas. It's perfectly inert for this job. It gives you a stable arc, helps ensure good weld quality, and critically, it prevents those harmful oxides forming in the weld. Now, if you were to use those other options like A, C, or D, which contain CO2 or oxygen, well, they would react.
Bad news for aluminium.
Very bad news. You'd get significant oxidation, probably lots of porosity, little gas bubbles trapped in the weld, and that just kills the weld's strength and integrity. So for aluminium GMAW, pure argon is the standard.
Right, that inert property is key. Non-negotiable for a clean aluminium weld. But I have heard sometimes people use argon mixed with a bit of helium for aluminium. Why wasn't that an option, maybe? And what's the deal with helium?
Good question. That shows you're thinking about the nuances. And yes, argon-helium mixes are used, especially for thicker aluminium sections or maybe in automated welding setups. See, helium, it has a higher ionization potential than argon. It basically creates a hotter arc.
Okay, hotter arc, so deeper penetration.
Exactly. Better penetration, sometimes better fluidity in the weld puddle, maybe faster travel speeds, all useful things, especially on thick material where getting enough heat in is important. But helium is more expensive than argon, and you usually need a higher flow rate too, so it's less cost-effective for, let's say, general work or thinner plates. The question asked for a suitable gas, and 100% argon is the most common, widely applicable, and cost-effective primary choice. But knowing about the helium mixes definitely adds to your understanding.
That's a great clarification.
Yeah.
It really drives home how critical gas selection is. It's not just a small detail. It changes everything depending on the material and the thickness. An inspector needs to know these specifics, understand the why, and maybe even the when for alternatives like helium. Okay, we've looked at technique and gases. The how. Now, how do we ensure consistency, quality across a whole project, maybe with different welders, different machines? Question 3 takes us into the world of standards and specifications. BSEN 288 and BSEN ISO 15614 are specifications for. Are they for A, welder approval testing, B, welding equipment calibration, C, welding procedure approval, or D, consumables for submerged arc welding, right? Think about the world of welding standards, BSEN ISO. These bodies publish specifications for all sorts of things to ensure safety and quality. What area do these particular standards typically focus on in welding?
Okay, the correct answer is C. Welding procedure approval.
Procedure approval.
Yes. And this really brings up a vital point for any inspector. Why is standardizing the method, the procedure, so incredibly important for getting consistent quality and safety? These standards, BSEN 288 and the newer BSEN ISO 15614, they are absolutely key. They lay out the strict requirements for qualifying what's called a welding procedure specification, or a WPS.
The WPS, right. That's like the recipe for the weld.
Exactly like a recipe. It details everything: the welding process, the specific base metals, the filler materials, essential variables like preheat, interpass temperature, voltage, amps, travel speed. You name it. When a procedure is approved according to these standards, it means you have documented evidence that if you follow this specific recipe, the weld should consistently meet the required quality and mechanical properties. It's very different from welder approval, option A. That focuses on the person's skill in following a qualified procedure. This is about validating the procedure itself.
It really makes you think, doesn't it? Without these validated procedures, fabrication could be totally unpredictable. It's like the hidden framework ensuring things are built right. So for an inspector, knowing these standards means you're checking that the recipe itself has been proven to work. It's foundational. Let's shift now to heat treatment. This is where we intentionally change the steel's properties using heat. Typical temperatures used for normalizing a CMN steel plate are, is it A, 600, 650 degrees CB, 700, 800 degrees Cers, 700, 800 degrees Cers, 700, 800 degrees Cers, 800, 800 degrees Cers, or D, 800, 920 degrees Cer. Think about why we normalize steel. What are we trying to achieve inside the metal at a microscopic level? And what temperature range would likely be needed to make those changes happen effectively?
The correct answer here is D, 880 to 920 Celsius.
Right. Normalizing is a really common heat treatment, especially for carbon manganese or CM steels. Its main goals are, well, several things, really. Refining the grain structure, making the internal structure more uniform or homogeneous, and as a result, improving mechanical properties like toughness and ductility. And that specific temperature range, 880 to 920 C, is absolutely critical.
Yeah.
Why? Because that ensures the steel becomes fully austenitic.
Austenitic, meaning it transforms into that single-phase structure.
Exactly. You heat it up until the entire structure transforms into austenite. Once it's soaked at that temperature long enough for the whole piece to reach it, You then take it out of the furnace and let it cool in still air. That air cooling is slower than, say, quenching in water or oil, and this relatively slow cooling allows a fine, uniform mixture of ferrite and perlite to form from the austenite. It's this fine, uniform grain structure that gives you the improved toughness and ductility you're looking for. If you go too low with the temperature, you won't fully transform to austenite. If you go too high, the grains might start to grow too large, which actually hurts toughness. So that range is the sweet spot.
Wow, the precision involved is quite something. It's not just get it hot, it's get it to exactly the right state to achieve those specific microscopic changes. So what happens, practically speaking, if someone messes up and normalizes at, say, 700 degrees, option C? What kind of problems would that cause, and what might an inspector look for?
Okay, yeah. Normalizing at 700 degrees C would be a problem because that's generally below the temperature needed to fully transform CMN steel into austenite. You wouldn't dissolve all the existing structures properly, you'd get an incomplete transformation. This means the grain refinement you want wouldn't happen properly, if at all. The homogenization wouldn't occur. So the steel's properties, especially toughness and ductility, likely wouldn't improve as intended. It might remain somewhat brittle or inconsistent. An inspector. Well, first you check the heat treatment records, the charts, to see if the specified cycle was actually followed. If there's serious doubt, you might need to look at further testing, maybe hardness checks, or even destructive tests like Charpy impacts to verify if the material actually has the properties it's supposed to have after normalizing. It's about confirming the material's internal structure is correct.
It really is a science. Understanding those metallurgical changes is just so fundamental to ensuring the material is fit for purpose. Okay, final question for this deep dive. And this one, this gets right into material science, weldability. Why some steels are trickier to weld than others. Here's where it gets really interesting. The maximum hardness in the HAZ of a steel will increase if. Will it increase if? A, heat input is increased. B, CEV is increased. C, joint thickness is decreased. Or D, basic electrodes are used. Okay, think about the heat affected zone, the HAZ, that area right next to the weld that gets heated but doesn't melt. What influences its final microstructure and hardness, especially considering the fast cooling that often happens in welding?
Right, the correct answer here is B. CEV is increased.
CEV, carbon equivalent value.
Exactly. And understanding CEV connects directly to the bigger picture of predicting weldability and, crucially, preventing nasty defects like cracking. CEV, or carbon equivalent value, it's essentially a measure of the steel's hardenability. How easily it can form hard structures when it cools quickly. It's not just based on carbon content, though that's a big part. It also accounts for the effect of other alloying elements, manganese, chromium, molybdenum, vanadium, nickel, and so on. They all contribute. So a higher CEV means the steel has a much greater tendency to form very hard, often brittle, microstructures, specifically things like martensite in the HAZ during that rapid cooling cycle typical of welding. More martensite means higher maximum hardness in the HAZ, and critically, a higher CEV significantly increases the risk of hydrogen-induced cracking, also known as cold cracking.
Okay, so higher CEV equals higher hardenability equals harder HAZ equals higher risk.
That's the chain, yes. Now let's contrast that with option A, increasing heat input. Generally, putting more heat into the weld slows down the cooling rate of the HAZ, right?
It takes longer to cool.
And a slower cooling rate usually gives the steel more time to transform into softer structures like ferrite and perlite instead of hard martensite. So higher heat input usually reduces maximum HAZ hardness, not increases it. So the CEV is the direct factor here, indicating an increase in potential HAZ hardness.
That's a really important distinction. Different factors pulling in opposite directions. So for you, the welding inspector, looking at a material specification, seeing that CEV number, how does knowing that practically help you manage risk before or during welding?
Oh, it's absolutely fundamental for managing risk. If you see a material certificate or a WPS referencing a steel with a high CEV, alarm bells should ring, well, maybe not alarm bells, but flags should go up. You immediately know this steel is more sensitive. It's more likely to form that hard, brittle HAZ and potentially crack if you're not careful. So that knowledge directly informs your decisions or the decisions you ensure are being made. Things like requiring a higher preheat temperature before welding starts.
Right, slow down the cooling from the start.
Exactly. Maintaining minimum interpass temperatures, not letting the part cool down too much between weld runs, and potentially specifying post-weld heat treatment, or PWHT, to temper that hard structure afterwards. All these actions are aimed at controlling the cooling rate, preventing the formation of excessive martensite, and reducing the risk of hydrogen cracking. The CEV isn't just a number. It's a predictive tool for ensuring weld integrity.
Fantastic. And with that explanation, we've actually covered some really critical ground today, haven't we? We walked through 5 key questions typical of the CSWIP 3.1 exam. We looked at distortion control with backstepping, the essential role of argon for aluminum, the absolute necessity of procedure standards, the specifics of normalizing steel, and finally, how CEV dictates HAZ hardness and weldability. We really hope this deep dive, focusing not just on the what's but the why, has been genuinely helpful for you, both for the exam and for your career ahead.
Absolutely, because the real goal here, it isn't just ticking boxes on an exam paper, is it? It's about building that solid mental framework, understanding why these things work the way they do, how they all connect in the real world of fabrication. So as you continue studying, maybe think about this. How does the knowledge we've covered today, everything from controlling distortion way back at the start to understanding hardenability with CEV just now, how does that empower you? How does it let you move beyond just spotting a defect to actually understanding its root cause, maybe even predicting where problems might occur, and crucially, knowing what steps are needed to prevent them in the first place? That deeper predictive insight. That's what truly makes an outstanding, indispensable inspector. Keep asking questions, keep digging deeper, and keep building that knowledge.